Hello class, this is Mr. Lehman. Today I want to take a look at something called percent yield and review something that we've done before, and that is percent error. So first, percent yield. So percent yield has a formula. So percent yield is basically a measure of how much of a product you produced compared to, in theory, what you should have been able to produce through a lab experiment. So ideally you should be able to get 100%, but because of flaws in lab technique, or just the actual chemical process itself, you may not be able to get 100%. So sometimes like 60, 70% yields are actually pretty good. Alright, so the way that we calculate percent yield is what we call the actual. Now the actual value is what you actually get while working in a lab. So you and your lab group are doing a lab. When you're all done, you make your final measurements. It's how much product is left in the beaker on the filter paper. Alright. We're going to divide that number, what you get in the lab, by the theoretical value. Alright, the theoretical value for how much product you should have been able to produce comes from our calculations, comes from our stoichiometry work. Alright, so we're going to work through a problem. We'll apply this formula to figure out our percent yield. Percent error, something that we used before, is, remember, absolute value so same things up here. You're going to take your actual value, what you get in the lab, what you get for your measurement, subtract theoretically what you should get, and that's what, once again, what we get through our calculations. And then the key thing here, once again, this is negative. You drop the negative. We want only a positive value. We got to divide by the theoretical again. So remember, we want to figure out what percent we are off from what, in theory, we should have gotten. So we always divide by the theoretical value. So theoretical bottom for both calculations is in the bottom. The nice thing is if you add these two numbers up, these two numbers, assuming your percent yield is under 100%, these two numbers should add up to very, very close to 100%, if not 100%, depending on where you round and sig figs and that. Alright, so let's look at a reaction. Alright, this is one that we also looked at in our notes here in our big white packet. So it's currently question 11. Depending on whether or not I made any revisions, it may be a different question number, but it is in your package. So CS2, carbon disulfide, oops, wrong button, I apologize. Carbon disulfide is going to react with oxygen in the air, which is found in pairs, is diatomic, to make carbon dioxide and sulfur dioxide. The equation in our packet is already balanced. So 3 oxygens here, 3 pairs of oxygen here, 2 moles of sulfur dioxide there. So 1 mole of carbon disulfide will react with 3 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of sulfur dioxide. Now the question says, when carbon disulfide burns, we produce these two things. What is the percent yield of sulfur dioxide if the burning of 25 grams of carbon disulfide produces 40.5 grams of sulfur dioxide? So, looking at that question, it's telling us that we're burning 25 grams of carbon disulfide, and it's telling us that actually in the lab we're making 40.5 grams of sulfur dioxide. So that's our lab value. That's not our stoichiometry value. So what we want to do for percent yield is figure out, well, based on our calculations, these two things aren't mentioned. So CO2 is a byproduct. We're not worried about it. Oxygen, we're assuming that there's excess in the environment. So it says 25 grams of this chemical can make how much of this product. Once we have that number, that's our theoretical value, we then can compare it to our actual value, what we got in the lab. So 11A, so we're going to go ahead and do some stoichiometry. 25 grams of CS2 divide by the molar mass of what we know. So this is what we know. And the molar mass of a carbon and 2 sulfurs, 12.01 plus 2 times 32.07, 76.15. The ratio, what we're converting into, we're making 2 moles of product for every 1 mole of reactant. So you might be wondering, how can that be? Think about it here. So carbons aren't in this chemical, so you don't have to worry about the carbons, but the sulfurs, there's 2 sulfurs per every one of these. Our product only has 1 sulfur, so because every one of our reactants supplies 2 sulfurs, in theory, for every one of this chemical, we can make 2 of this chemical. That's why it's that 2-to-1 ratio. And then the last step is to multiply by the molar mass, since the sulfur, oops, I got talking there and I put the wrong number of oxygens as SO2. So sulfur dioxide, 32.07 plus 32, 64.07 grams of SO2 per mole. Units are canceling, so go ahead and pause this, see what you get as an answer, and then unpause. Welcome back. 42.1 grams of SO2 in theory can be produced from 25 grams of CS2. 3 sig figs here limits us to 3 sig figs here. So in the next part B, 11B, we want to figure out the percent yield. So we take what we got in the lab, and so it tells us your lab group produced 40.05 grams of SO2. Divide that by what we actually produced, or what we actually calculated we should have been able to produce, excuse me. Our stoichiometry says 42.1, so stoichiometry number always goes on the bottom. We're going to multiply this by 100 to make it a percent. I may have forgot that in the opening. But yeah, we got to multiply it by 100% means per 100. And 40.5 divided by 42.1 times it by 100. We get 96.2% yield. So in the lab we made 96.2% of what we calculated we should have been able to make. Alright, percent error. If we want to do a percent error calculation, we're going to take what we got in the lab, subtract it from what stoichiometry says we should have been able to get, divide it by what stoichiometry says we should be able to get, and times it by 100. So we can simplify here to look at sig figs. So 40.5 divided by 42.1 is 1.6. We only can keep one decimal place when we subtract. Divide that by 42.1, times it by 100, and so we're taking 2 sig figs, 1.6, and we're dividing it by stoichiometry number 42.1, times it by 100, and we get 3.8% error. Which is awesome, right? That's awesome because, as I mentioned earlier, your percent error and your percent yield, if the percent yield is less than 100%, when these two things add together, they should add up to 100% or very close to 100%. If your percent yield is over 100%, and that's possible, like if your chemicals and dryers are impure, things like that, then because this number we're dropping to negative, it might not add up to 100%, it might be over 100%. So it's something to look out for. Hopefully this helps. And as always, if you need help, stop on by, and have a great day, everybody.